So remember, ionization energies, it's the amount of energy that we need to remove each electron from your atom. So I can take all the ionization energies and I can plot them on a graph. So if I place the energy on the y-axis and then the number of electrons removed on the x-axis, so this would be the first electron removed, then the second, third, etc., until there's no more electrons left for each atom. So we can plot the energies on a graph and we would start to see a trend. So something like that. And by reading these energies on the graph like that, we're able to tell things about the atom. So for example, like what group it's in. So you can see the lowest amounts of energies here. Those are the energies in the outermost shell that are furthest away from the nucleus. So the amount of electrons that are there with the lowest energy before there's a jump, that can tell you what group your atom is in. Because there's 2 electrons here with very low energies, so those must be in an energy level all by themselves, all the way at the edge of the atom, far away from the nucleus. So because there's 2 here, that means this must be in group 2. Then the next jump would be to the next energy level closer to the nucleus. Okay, because the closer you get to the nucleus, the more attracted it becomes. So here, there's 8 electrons, all with similar amounts of ionization energy, so they must all be in the same energy level. And then our next jump to the highest amount of energy that it takes to remove the electron means that these 2 must be in our closest energy level to the nucleus because the amount of attraction is super high. So that means our forces of attraction are pulling those electrons close, and it needs a lot of energy to remove those 2 because they have the highest amount of energy. So that'll tell you how many energy levels they are and what group our atom is in. If we look at a different version of an ionization energy graph, we can also plot the ionization energies going across a period for just the first ionization energy. So that's just to remove the outermost electron. So if I look at my energies from sodium to argon, they also follow a trend. So if we connect them all, our general trend is going up. So as we go across our period, it gets harder and harder to remove electrons, okay, because as we go across, we increase in proton number. So as we increase in proton number, we're increasing the positive charge in the nucleus, and by increasing the positive charge in the nucleus, it attracts those electrons even more. And because these are all in the same energy level, there's not going to be any shielding, so we get a stronger force of attraction, so it becomes harder and harder to remove from the first going all the way across to that last one. But there is little dips, and we need to be able to explain why there is dips and why it doesn't just go straight up. So the first one would be between phosphorus and sulfur over here. So you would expect, because sulfur is 16 electrons and 16 protons, that it should be higher than phosphorus, which is only 15, but it's not. The energy to remove that outermost electron is lower. And we can explain that by looking at the box diagram. So if you look at the box diagram for phosphorus having 15 electrons, and we fill them in, so we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Remember, we always half fill. So for phosphorus, that means that in the 3p orbital, they're only half full. But as soon as we get to sulfur of 16, we add 1 more electron there. And then we filled 1 orbital. Now electrons are negative, So when they're together, they repel each other. So this one pair causes what's called electron pair repulsion, and it means that that extra electron there is being repelled by the others, making it easier to remove. So that's why your sulfur has a lower first ionization energy than our phosphorus, just because of that one extra electron. And then similarly, that other bump over there between the magnesium and the aluminium also has to do with our energy levels, because magnesium is 12. So that means we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so that ends there on the 3s2. Okay, but the aluminium adds one more, meaning it has 3p1. So because it's got that extra electron in the p orbital being further away than the s orbital, which is now full for magnesium, makes it slightly easier for aluminium to lose that one electron in the p orbital, because it's there on its own further away, as opposed to the magnesium, which has full shells. And that's how we explain those two anomalies on that graph, as well as the general trend of ionization energy.